Okay, so the next question that we have here is example number 5, which is show that the relation R in the set Z of integers given by, so you want to show that basically the relation R, in the set Z of integers, given by R is equal to all the ordered pairs A and B, such that 2 divides basically A minus B, is an equivalence relation. So you want to show that R is an equivalence relation. So about basically an equivalence relation, we said that a relation is an equivalence relation if basically a relation R, let's say, is an equivalence relation if basically number 1, R is basically symmetric, and also number 2, R is basically symmetric reflexive, and number 3, R is transitive. Right, so that is basically, so that means that if that relation is symmetric and reflexive and transitive at the same time, then you can call that relation an equivalence relation, right? So now let's see how we can, so that means that if you can show that R is symmetric and R is reflexive and transitive, then that basically means that R by definition R is an equivalence relation. So how can we do that? How can we show that, for example, R is symmetric, reflexive, and transitive? So let's try to think through this problem. So here we are saying that basically the relation R is in the set Z, meaning that we are working in the set of integers. So basically we are working on the set of integers, right? So the set of integers would be Z is equal to basically 0, 1, 2, and 3, and so on and so forth, and then you have negative 1, negative 2, and negative 3, and going all the way up to negative infinity, and going all the way up to positive infinity. That is the set that we have here. And then as the relation in this set, we have basically R is equal to all the ordered pairs A comma B, such that 2 divides A minus B. We have R is equal to all the ordered pairs A comma B, such that 2 divides A minus B, right? And you want to show that R is an equivalence relation. So this situation is basically this way, meaning that if you want to be able to, of course, to be able to solve the problem, you need to know what you're working on. And so let's go through this step by step. Okay, so now in order to understand this problem, so basically you have the you can imagine that you have the set of integers, meaning that you have basically z over here, and then you have z over here as well, and then you have basically the set of integers over here, which is z again, and z by definition, as you know, is basically this set of numbers. Now, when you create the Cartesian product of z and z, you will get basically every element of this set will be related to every other element of this set, meaning that, for example, suppose that you have 0 in here. 0 will be related to every other of every number in this course, in this set. Again, you have, for example, the number, for example, 1. 1 will be related to every number in this set. You have the number, for example, 2. The number 2 will be related to every number in this set, and so on and so forth. Okay? That means that you will have basically an infinite number of ordered pairs. So each of these lines represent an ordered pair. For example, suppose that in this particular case, 0 goes to, for example, positive 1. Then for that you will get an ordered pair 0, 1. And suppose that 0 goes to positive 2, for example. Then you will get an ordered pair 0, 2, and so on and so forth. So you will get this set of A, comma B of these ordered sets of these ordered pairs, which is 0, 1, which is basically 0, 1, for example, 0, 2, and so on and so forth, and you will get basically an n number of, or an infinite, now you could say an infinite number of such pairs, such ordered pairs, right? Now, you know that the relation is basically a subset of this set. So a subset of the Cartesian product of z and z based on some rule. For example, in this case the rule is that 2 divides a minus b. Then basically R is going to be a subset of this set based on this rule, meaning that you will have all the, basically based on this rule, what you will do is that you will take all of the ordered pairs in which case this rule applies, and then all of those ordered pairs will be basically a part of this set. For example, A1 B1 and A2 B2 and so on and so forth, right? So for example, among these ordered pairs, you would have, for example, something like, for example, 6 minus 6 and 8, for example, or 8 and 6. So you would have 8, 6, right? So 8, 6 is the same thing as 8, 6. If you calculate a minus b here, this is a and this is b, and so a minus b is equal to 8 minus 6, which is equal to 2. Now you can see that 2 divides this number, or this number is actually divisible by 2. Or you could say that, for example, you could have an ordered pair like, for example, 14 and 14, for example, 6. 14, 6. Now in this case, a minus b is equal to 14 minus 6, which is equal to 8. you can see that 8 is divisible by 2, or you can say that 2 divides 8. So this is also a pair that you would find in the set R. Now, when it comes to basically negative, so basically, so as you can see, if A and B are both positive even integers, so if A and B are both positive even integers, then basically A comma B belongs to R. Now let's basically let's test another couple of numbers. The set of integers does have basically positive even, not even, but odd integers as well. We have the positive odd integers as well. So the positive odd integers would be, and basically you do need to, first of all, you need to decide whether you actually need to decide basically this process or not. So basically what I'm doing here is that I'm trying to find out what sort of members of the set Z would satisfy this condition here. And I suppose we can start by we can start by answering one of these questions, and then we will know whether we actually need to go through this process or not. So let's see how that works out. Okay, so it turns out that it's actually not necessary to know the particulars of these numbers and so on and so forth. So what we can do, we can actually go and basically test all of those conditions, meaning that you have basically the relation R. You have the relation R on Z or in Z, and basically R is defined by all the ordered pairs A comma B such that 2 divides A minus B, right? Now, first of all, for R to be reflexive, we have for all A belonging to the set A, we have A comma A belongs to R. If that's the case, then you can say that R is reflexive. Now you can see that, let me close my window. Okay, so you can see that basically you can see that for all A belonging to the set of integers, then you can see that basically A minus A, so basically you have, let's suppose that we have A and A basically as a part of A and A as a member of, let's suppose that we have A and A as a member of R. Let's see what happens. So A comma A, if A comma A belongs to R, then we have basically A can be, and then we have basically the condition is that basically if this condition is fulfilled, then that means that A comma A can belong to R, otherwise not, right? So now basically a minus a would be, you have a couple of cases. For example, a can be equal to 0, or a can be a positive integer. A belongs to the set of integers and a is greater than 0, or you can say that a belongs to the set of integers and a is less than 0. In any case, it doesn't really matter, because if a is equal to 0, then a minus b in this case would be the same thing as a minus a, right? And a minus a would be basically 0 minus 0, which is equal to 0. Now when you say 2 divides a minus b, and this is now a minus b. So when you say 2 divides a minus b, that means that this number has to be divisible by 2, which is actually the case. So we have no problem here. Now if a belongs to the set of integers and a is greater than 0, meaning that it's a positive integer, then suppose that, for example, a is equal to, I don't know, 2. Any number you can take. Then you will end up with a minus a, which is equal to 2 minus 2, which is equal to 0. And again, 2 divides this number. So again, you have no problem. Being a negative number, let's say that, for example, a is equal to negative 2. Then negative 2 plus, or negative 2 minus negative 2 is the same thing as that is a minus a. So negative 2 minus negative 2 is equal to negative 2 plus 2, which is equal to 0. Again, 2 divides this number. Which means that you can say that for all a belonging to the set of integers, a comma a belongs to R. Which means that basically R is reflexive. R is reflexive. Now, one more thing that we need to check here is whether R is symmetric or not, because we are checking for whether basically R is an equivalence relation. The 3 of them have to be the case. So let's see if R is symmetric. Okay, so to check whether R is symmetric, it is actually very simple. But in case, if you understand the logic behind it, otherwise it's not very simple, meaning that I had to just think for like 20-25 minutes, and then I came to the conclusion that, well, I didn't have to basically consider all of those cases. So now I'm just going to give you a summary of what I did, because it's basically not really it's not really worth your time to know everything that I did. Now, to check whether R is symmetric, the condition is that a1 comma a2 belongs to R. Then a2 comma a1 also has to belong to R for all a1 and a2 belonging to A, right? Now, if basically in this particular case, you can argue that, for example, let a comma b belong to R, meaning that some 2 numbers belonging to the set of integers belongs to that relation, to that specific relation. Then that relation is telling us that is basically all the ordered pairs a comma b, such that 2 divides a minus b. That means that a minus b is divisible by 2. So what that means is that if basically if a1 comma a2 belongs to R, then that means that a minus b is divisible by 2 based on the rule that we had up there. And so now we have to make sure that all the ordered pairs b comma a also belong to R in order to show that R is symmetric. Now, how can I make sure that all the ordered pairs b comma a also belong to R? we need to make sure that b minus a also is divisible by 2, right? Because if this ordered pair has to belong to R, based on the rule that we have, a minus b has to be divisible by 2. If this ordered pair is supposed to belong to R, then b minus a has to be divisible by 2. Because over here we are saying that if we have this ordered pair a comma b, meaning that the first number is a, the second number is b, then a minus b is supposed to be divisible by 2. Meaning that you take the number a and the number b and subtract b from a, and that has to be divisible by 2, right? Now there are some typical cases here in the set of integers, where if you take some two numbers a and b from the set of integers, then a minus b is divisible by 2. Meaning that you could argue that, let me erase this thing because I don't really need it anymore, and that makes things unnecessarily complicated. So basically the set of integers is just all of these different categories, meaning that you have positive integers, you have negative integers, and you have the 0 in the set of integers. Okay, so what that means is that basically if I denote these by, for example, category 1, 2, 3, 4, and 5, I have the even positive integers, I have the odd positive integers, I have the even negative integers, odd negative integers, and I have the 0, right? Now if I consider, for example, 1, now what I need to do is basically I want to find out in which of these cases basically a minus b is going to be divisible by 2, So suppose that, for example, you have 1 with 1. You consider 1 with 1, meaning that you have an even positive integer and another even positive integer. Meaning that, for example, you have a 2 and you have another 2. Meaning that your a is equal to 2 and your b is equal to 2. Then a minus b becomes 2 minus 2, which is equal to 0. 0 is divisible by 2, by 2 of course. And, well, there are some cases here that if you consider them, they will not be divisible by 2, meaning that, for example, if you consider even positive integers and 2, which is odd positive integers, and even positive integer would be, for example, a 16, and an odd positive integer would be for example, a 15, right? So 16 minus 15 is equal to, for example, 1, which is not divisible by 2, so it doesn't work there. So you can consider 1 with 1, 1 with 2, 1 with 3, 1 with 4, and then you can consider 2 with 1, 2 with 3, 2 with 2, 2 with 4, and then 3 with 1, 3 with 2, 3 with 3, 3 with 4. And then you can consider 4 with 1, 4 with 2, 4 with 3, 4 with 4, and of course you're not supposed to repeat anything, meaning that if you consider something 1 with 4, for example, then 1 with 4 and 4 with 1 would be the same case, so you're not supposed to consider that. So once you do that, you will get all of these different cases, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, all of these different cases, and you can actually calculate the number of cases that you will get with it seems that actually 5 combination 2 works here, meaning that I didn't think that, well, you see over here you can actually consider 1 with 1, right? So you would think that, for example, 5 combination 2 would not work here, but 5 combination 2 is 5 factorial, 5 minus 2 factorial times 2 factorial. which is equal to basically 5 factorial 3 factorial times 2 factorial, which is equal to basically 3 factorial times 4 times 5 over 3 factorial times 2, and then you can cancel these two out, and then you will get a 10, which is exactly the number of the cases that you get here, right? Now, what's important here is that you get all of these cases. In some of these cases, basically, A and B will be basically the order per A comma B is a member of R, and in some of these cases A comma B is not a member of R because it's simply not divisible. Meaning that if you try A minus B, you will get some number which is not divisible by 2, which means that the order per A comma B in that case is not a member of R, right? Now in all of those, well, of course, whenever that happens, whenever this sort of thing happens, which is basically the order per A comma B is not a member of R, then of course you don't have to worry about anything else anymore, because if it's not a member of R, then you don't have to check whether B comma A is also a member of R. It was not a member of R in the first place. Let me close my window. So basically the logic is that whenever basically A comma B is a member of R, so then you have to check whether B comma A is also a member of R. But whenever it's not a member of R, it's not a member of R, and so you don't have any problems because it was not a member of R in the first place, right? So now the point here is that, of course, it took me around 30 minutes to write down all of these cases and then examine all of the different cases, and of course I should have used I probably should have used algebra in order to examine all of those cases, but it was not really necessary, because in all the cases where A comma B is a member of R, meaning that in this case and 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 in this case, right, then B comma A is also going to be a member of R, because, for example, let's say that, for example, in this case, if I take 1 with 1, meaning that if I take two even positive integers, would be 16 and 14. Now 16 minus 14 is equal to 2. It's divisible by 2. Now the other way around, if I calculate 14 minus 16 is equal to negative 2, it's again divisible by 2. So you have no problem. As another example, let's say that you take this case over here, 2 with 2, meaning that you have two odd positive integers. So two odd positive integers would be 3 and 3, for example. 3 or 5, for example, right? Now if you take a 3 and 5, what happens is that 3 minus 5 is equal to negative 2. 5 minus 3 is equal to positive 2. So in both cases it's going to work for you. You have no problem. And you can test for all of these cases and you will have the same conclusion. Meaning that whenever A comma B is a member of R, then B comma A is also a member of R, which means that basically you can say that basically R is symmetric. R is symmetric. Now what I'm going to do is that I'm going to write down all of these cases, because we might actually need all of these cases in some other example, meaning that if you have, for example, if there is the case that you are subtracting that you're subtracting an even positive integer from an even positive integer, is that number going to be divisible by 2 or not? If you're subtracting an odd positive integer from an odd from some even positive integer, from even negative integer, for example, is that number going to be divisible by 2 or not, and so on and so forth. All of these 10 cases. I'm going to write them down in a separate article on my blog, and then you can refer to that whenever you need to. I'm going to share a link to that article in the description of this video. Okay. So let me write these down, and then I can erase them, and then we will get to the rest of this problem. Okay, so now I have actually noted them. I have written them all down, so I can erase all of these things, and we can get to the rest of this problem. So now the next thing that we need to figure out here is basically whether R is so here we figured out that R was symmetric. So here R was reflexive, and symmetric, reflexive, and transitive. Now to check whether R is transitive. So how do we do that? So the condition that we use for transitivity of a relation, we say that basically if basically A1 comma A2 belongs to R, and A2 comma A3 belongs to R, that implies that basically A1 comma A3 also belongs to R. A1 comma A3 also belongs to R for all basically A1, A2, and A3 belonging to the set A. Right? Now, and remember that when I write the set A over here, what I mean is the set under study. For example, the set under study in this case is, as you know, is the set of integers, for example. And when I write here basically A1 and A2, that's any two A1, A2 belonging to R, and then A2, A3 is any A2, A3 belonging to R, to that relation defined here, meaning that, for example, in this particular case, the relation that we have is that, for example, all the ordered pairs A, comma B, such that 2 divides A minus B, for example. That's our relation here. And depending on this rule that you see over here, some A, comma B's do belong to R, some A, comma B's do not belong to R. So it's simple to decide that. And then the whole thing is clear. So it's I write this only as a condition, right? As a general condition, I mean. Now you want to check whether R is transitive or not. So now in this particular case, if some A1, comma A2 belongs to R, and so now let me think about this problem. Okay, so now basically to check whether R is transitive or not, basically this is the condition for transitivity of R, meaning that if A1 and A1 comma A2 belongs to R, and also A2 comma A3 belongs to R, if that implies that basically A1 comma A3 belongs to R for all basically A1, A2, A3 belonging to A, then that means that basically R is transitive. Now, over here, let's assume that basically some let's say A1 comma, for example, A1 B1, for example, right? The example that we had over here was let's say that some A1 B1, let's say that's A1 comma B1 belongs to R, right? And let's say that and also that's some B1, let's say that some B1, for example, B1 B2 also belongs to R. Now, if that is the case, now if that assumption is true, now if basically A1 comma B2 also belongs to R, then you can say that R is transitive. You see, basically, I hope that you have understood my logic. The logic that I have used is that I have used this condition in order to show that R is transitive. So this is telling me that if A1, A2 belongs to R and A2, A3 belongs to R, meaning that over here I have A2, over here I have A2, and over here I have A1 and A3. If that's the case, then you can say that basically R is transitive. So the assumption that I have made is that I have assumed that A1, B1 belongs to R, and B1, I have the same numbers over here, B1, or the same variables over here, B1 and B1, B1 and B1, and then A1 and B2. So I have made this assumption, and then I'm saying that if this is the case, which is the second part of this condition, if this is the case, A1 comma B2 belongs to R, then R is transitive based on this condition, right? Now, it's of course easy. It's of course possible to figure out a couple of cases, simple cases based on simple examples. For example, if I want to know what happens if I add, for example, a positive integer to a positive integer, of course then I can take, for example, a 2 and add it to a 3, and then I can conclude that 5. So then I can conclude that when you add a positive integer to a positive integer, you'll get a positive integer. Or if I want to know that, for example, what happens if I add an even positive integer to an odd positive integer, then I can conclude that I'll get an odd positive integer, right? And these are the kind of things that in integers at least don't change, meaning that you can just keep on going, trying different positive integers, try different odd positive integers, try different basically even positive integers, and the same thing keeps happening. So you can trust that, of course, as long as you know what you're doing, meaning that testing a couple of numbers doesn't constitute a proof in any way, shape, or form, of course, never, of course, because you simply don't know, meaning that there might be at least one case in which basically what you're saying is not true, which means that then what you're saying is actually never true. So what that means is that So what that means is that now in the case of this situation, I want to know if A1 B1 belongs to R and B1 B2 belongs to R. And what that means is that basically if A1 B1 belongs to R means that basically A1 minus B1 is divisible by 2 based on this situation. Based on the condition that we have in R, we said that if A and A comma B has to belongs to R, then 2 has to divide basically A minus B, meaning that A minus B has to be divisible by 2, otherwise A comma B cannot belong to R, right? So what that means is that, so this is the condition. So what that means is that if I'm assuming that A1 comma B1 belongs to R, that means that A1 minus B1, so this assumption over here means that basically A1 minus B1 is divisible by 2, or 2 divides basically A1 minus B1, right? And also this assumption implies that basically B1 minus B2 is also divisible by 2. Is divisible by 2, or basically 2 divides B1 minus B2. Now I want to know if that is the case, which is basically my assumption. If that is the case, then if A1 minus A1 comma B2 belongs to R, meaning that if basically A1 minus B2 is also divisible by 2, right? So now in order to do that, you need to simply use some algebra and, well, actually prove it logically using algebra. And in order to prove that, in order to see what sort of result you can expect if A1 minus B2 is divisible by 2, which means that A1 minus B2 is an even number. And when you say that B1 minus B2 is divisible by 2, that means that B1 minus B2 is an even number, right? So now, since these two are even numbers, I can express basically A1 minus B2 as for example 2m for some integer m. You know that and the reason for that is that basically B1 minus B2 is an even number, right? For the same reason I express A1 minus B2, this is actually supposed to be A1 minus B2. So I express A1 B2, right? Okay, so I express A1 minus B2. Since it's an even number, I express it as 2m for some integer m. And you know that every even number can be expressed as 2m for some integer, meaning that, for example, if you have a 4, you can write it as 2 times 2. If you have an 8, you can write it as for example 2 times 4. 2 is always there. If you have a 16, you can write it as 2 times 8. But if you have a 7, you can write it as 2 times 3 plus 1. Or if you have a 5, you can write it as 2 times 2 plus 1. Meaning that if you have an odd number, then you can express it as 2n plus 1 for some integer n. And if you have an even number, you can express it as 2m, for example, for some integer n. That you can always do, right? So I have done the same thing over here, meaning that I have written basically a1 minus b2 as 2m for some integer m. Okay. Okay, so now basically we have written a1 minus b2 as 2m for some integer m. And so by the same logic, what we can do is that we can express basically b1 minus b2, b1 minus b2, a1 b2. There's something wrong here. You see over here I have written a1 b1, b1 b2. So that means that a1 minus b1 is divisible by 2 and b1 minus b2 is divisible by 2. So that means that a1 minus b1, I did make a mistake here many times. I apologize for that. So then I can say that a1 minus b1 as 2m for some integer as a1 minus b1 is even. And I can express b1 minus b2 as, for example, 2n for some integer n, right? Now my goal is here to check to see what happens to a1 b2, right? So if basically if a1 b2 if a1 comma b2 belongs to R, then of course a1 minus b2 is supposed to be is an even number, meaning that it's divisible by 2. If that's the case, then a1 minus b2 is an even number. So you can see that over here I have a1 b1, a1 b2, and a1 b2 over here. So I know that I do not really know if a1 minus b2 is an even number. I've just written that if that's the case, then that's going to be the case, but I don't really know. What I know is that basically I can write a1 minus b1 as 2m and b1 minus b2 as 2n. So I know that basically a1 minus b1 is equal to 2m, and I know that b1 minus b2 is equal to 2n, and these are my assumptions, therefore I know them. So now how can and I want to know what happens to a1 minus b2. So I have a1 over here and minus b2 over here, right? So I need to do something to these two equations, so that out of them I get basically a1 minus b2, and exactly that in terms of m and n. And of course b1 has to be cancelled out, otherwise it would be a nuisance. I don't really want it here, right? So you can actually do anything that you want, as long as what you do, what sort of operation you do gets you to this result over here. You can do whatever you want to do, meaning that you can add these two equations together. You can subtract this one from this one. You can subtract this one from this one. You can divide this one by this one, or divide this one by this one, or even you can even multiply them. It doesn't really matter, as long as what you do gets you to your objective. So now if I add these two equations just simply together, you can see that here I have negative b1, here I have positive b1, so they will simply be cancelled out, and then I will get a1 plus minus b2, which is basically exactly what I'm looking for. So adding these two equations together, I'll get a1 minus b1 plus b1 minus b2 is equal to 2m plus 2n. And you know that basically m and n are integers here. So then these two will be cancelled out, and you will get a1 minus b2 is equal to 2m plus 2n. You can write it as 2 times m plus n. And you know that basically m plus n, since both of them are integers, when you basically add two integers together, you will get an integer, meaning that you can write a1 minus b2 is equal to 2 times, for example, p, for example, for some integer p, right? Now since basically a1 minus b2, we were able to write it in terms of 2 times some integer, you can say that a1 minus b2 is an even number. Because it's basically the product of 2 and some integer. And it was actually our assumption over here as we started solving this problem. So what that means is that if a1 minus b2 is an even number, which means that it's divisible by 2, which means that a1 minus b2 is divisible by 2, which means that a1 comma b2 actually does belong to R, right? So so then here we can say that, so over here we said that we assume that a1 b1 belongs to R, b1 b2 belongs to R, and now over here we have, down here we have proved that a1 b2 also belongs to R. a1 b2 also belongs to R, a1 b2. That means that basically R is transitive, which means that R is transitive. R is transitive. So now we have shown that basically R is reflexive. So R is reflexive and symmetric and transitive. Therefore, R is an equivalence relation. Is an equivalence relation. Is an equivalence relation. Right? So that's basically this question here. This was example number 5. In the text there is only probably a couple of lines for the solution here, but as you can see, there is so much logic that goes into each of these exercises, and of course you need to understand them. Otherwise, I mean, it's just not possible to not understand mathematics. There is no other way of reading it, really. Now, there is some note over here. There is a note over here that says that in example number 5, which was basically this example over here, note that all even integers are related to 0. As, for example, so let me read this part and see what it's about. Okay, so now there is a couple of things. There is some theory that we can learn based on the example that we just did, example number 5. And we will discuss all of those in the next video. I'll see you in the next video. Thank you.